We've talked about projectile motion, and what we're going to focus on here is the range, which is considered the horizontal distance that the projectile will travel while it's in the air. For example, if a projectile is launched, this horizontal distance is considered the range of that projectile. And we found an equation in the previous lesson that gives us the height, the vertical displacement, as a function of constants and the horizontal displacement. And so what this is telling us is that if we ever know the horizontal position, this function will give us the vertical position associated with it. If we're interested in the range of the particle, the range is a special case. The range ends, the flight of the object ends, when the change in the y direction is 0. And so what we can do is look at this equation and see what happens when the height is equal to 0. And so we'll go ahead and write we have this equation. Now the thing is, this is a constant and these are constants. The only thing changing is our delta x. And we want to find out what values of delta x will cause the height to be 0, which means our projectile is landing, the flight is over, and we found our range. So we have a common term of delta x. We're going to go ahead and factor that out. And so what we have here is we have a second order equation. We have an x squared equation, a quadratic, second order polynomial, and that should have two solutions to it because of the square. And that's actually what we find here. What we have is one value times by another value, and if you have one number times by another number that gives you 0, that tells you that one or the other has to equal 0. Basically, if a times b equals 0, then either a or b must equal 0. So let's look at what that means. Well, delta x could equal 0, but that corresponds to the initial point. This delta x equals 0 means that we're at 0 height because we are on the ground about to be launched or in the process of being launched. So that is a solution, but we'd call that a trivial solution because that's not giving us new information. So we'll discard that one. We'll focus instead on this other part of the equation and letting this term equal 0. If this term minus that term equals 0, that tells us that this term must equal that term. And so we can rewrite that as well. Now, if we wish to find delta x, we can solve for delta x here. We're going to bring it over to the side, and we're going to write basically we've divided by this fraction, and so we're multiplying the other side by the reciprocal of that fraction. Now, one thing to note here, that tangent is actually a sine theta over cosine theta. And so that cosine theta on the bottom will cancel one of the cosine thetas on the top. And if we write our delta x, we will reorder it a little bit. You'll see in just a second. It doesn't matter what order we do our multiplication in. The reason why we did that is because this term is a trigonometric identity that equals sine of 2 theta. And so if we assume, what we see here, if we assume that the height is equal to 0, what the height as a function of the distance traveled, horizontal distance traveled, tells us is that the height is equal to 0 at the initial point. The height is also equal to 0 when delta x is equal to this value. V naught is a constant value, theta is a constant value, g is a constant value, so this is a constant range value that depends on the initial parameters of the launch of the object. This is telling us how far an object will go as it flies through the air. We found the range of an object, and we found that it depends on the initial velocity, the angle of launch, theta, and g. And so basically what we have is this range is actually a function of theta. If we imagine the launch velocity, the muzzle velocity is constant, and g is constant, this range depends on our angle theta. A few things that we can notice is that the range depends on the launch velocity, so if you shoot the object faster, it will go farther, which makes sense. It also shows us that the launch angle tells us how far an object will go. You can imagine if you shoot an object at different angles, it should probably go different distances, and that there's a dependence on g as well. So g is gravity on Earth. If we were on a planet with a heavier gravity, then this would be a larger number, the denominator, and the range would be smaller, because you wouldn't go so far if you were being dragged down to the surface of the other planet. On the other hand, if gravity is much less, a smaller number, the denominator, makes a much bigger range. One example of that is you've seen the footage of them playing golf on the moon, where the moon has a very low gravity, and so the astronauts were able to hit the golf ball something like a mile because the gravity was so small. They were able to hit the ball very far. But we imagine that gravity is dependent on the planet, which for our case is Earth, and our launcher, whatever kind of projectile launcher we have, will tell us about our initial velocity. But we do have this control over our angle theta, and it's not really clear what that is. So if we want to know how the range depends on our angle theta, we can look at what it takes, what angle theta will give us the greatest range, and see what that relationship is. If r is a function of theta, then to find out what angle theta will give us the greatest r is an example of maximizing a function. And the way that we maximize a function is to take the derivative of that function and set it equal to 0. That tells us where the max or min of that function would be. If we do that here, v naught and g are both constants. Here the derivative of sine will give us a cosine times the derivative of what's inside. The derivative of 2 theta would be a factor of 2. And for this to be a maximum range, our derivative has to equal 0, which tells us that we either have a maximum, and thus we have a horizontal tangent line, or we have a minimum, and we have a horizontal tangent line. Now, looking at these terms, none of these terms are 0. These are fixed values, and 2 is not equal to 0. So if this whole term is going to equal 0, that tells us that cosine of 2 theta has to equal 0. Well, if cosine of 2 theta equals 0, cosine equals 0 when, say, cosine of some angle phi equals 0 when phi is equal to 90 degrees. Right? Cosine of 90 degrees is 0, which tells us that our 2 theta must equal 90 degrees. If that's the case, then theta would be 45 degrees. That's the maximum, that's the angle that will give us maximum range. And that makes sense because that angle is basically in the middle of the ranges that you could of the range of angles that you could launch at. You could launch a projectile at any theta between 0 and 90 degrees, right? You could launch it perfectly horizontally, you could launch it perfectly vertically, or somewhere in between. One other thing that we notice here, besides this maximum value of the launch, is that the range depends on sine of 2 theta, sine of an angle. And we know that sine is positive in both the first and second quadrants. So basically sine is positive in the first quadrant and in the second quadrant. So for angles, sine of theta is positive for theta that is anywhere between 0 and 180 degrees. What that means, and we also know that if you are looking at the sine of an angle, and you have some angle here that is theta, and you have another line over here, you would measure a different angle, but you have the same reference angle. So you have the same angle theta between your line and the x-axis. What this tells us is that since sine is positive in both of these quadrants, that tells us that the sine of theta is equal to the sine of phi, where phi is measured in the second quadrant, something between 90 and 180 degrees. But phi is actually 180 minus theta. And so what we're seeing here is that the sine of an angle is equal to the sine of its supplement, of the angle on the other side. And you can test that for yourself. You can look at the sine of 30 degrees and the sine of 150 degrees, or the sine of 45 degrees and the sine of 135 degrees. Whatever pair of supplementary angles you want to look at, you'll see that those are the same. Well, what we're seeing here, though, is we're looking here, in our case, at the sine of 2 theta. And what we're seeing here is that the sine of 2 theta should equal the sine of 180 minus 2 theta, from what we talked about above. If that's the case, then that means that the sine of theta and 90 minus theta should give us the same sign, because we're going to end up doubling these values. And so we'll see shortly that this term is the same whether the angle is 30 degrees and 60 degrees, for example, or if this angle is 15 degrees and 75 degrees. If these are complementary angles, when we plug them into the sine of 2 theta, we see that they'll give us the same sine value, and thus they should give us the same range. When we look at ranges of projectiles, we found that the range depends on the initial velocity, the angle of launch, and the gravity. And we've seen that the motion of an object should follow a parabolic path with a different range and a different height depending on the particular direction of the launch. But we found this range to be true. We found that the maximum distance of maximum range for the launch of a projectile is at 45 degrees. And we've seen here that, for example, for 15 degrees or 75 degrees, we have the same range if we neglect air resistance. So in this case, the most of the velocity is horizontal, so the object is moving very fast horizontally, but it's not moving very far up or down, so it doesn't have much time to travel very, very fast. When you go very, very high up, most of your velocity is a vertical component, so you reach very high, you have a very high hang time, but you're not moving left or right very much during that time, and so you don't get very far. When those balance out, you end up at the same point. The same is true for 30-degree launch or 60-degree launch. These values converge at 45 degrees, which gives you the greatest range possible. We've also been assuming all of this time that air resistance is negligible, and thus we get a very, very nice, compact set of equations to talk about projectile motion. In many situations, though, this is a poor assumption to make. When you have a projectile that's larger or lighter, it tends to have more influence of air resistance. When you consider an object could be more aerodynamic or less so, could affect it as well as meteorological conditions, humidity, the density of the air, etc., can change the air resistance and, in fact, make the air resistance greater. So what we see in this picture is this is the, assuming no air resistance, this is the ideal case. We get a nice parabolic curve showing our projectile motion, and that's done in vacuum, so there is no air and there's no air resistance. However, if air resistance is actually taking place, that air resistance is a drag, and it's going to be pulling back on our object. And so as our object moves, it's going to have an initial velocity, but that initial velocity is being held back vertically. As the object tries to fly upward, the air resistance is pulling it down, which is going to reduce the height that it can reach. Reducing the height reduces the amount of hang time, the amount of time that the object is in the air, and will reduce the horizontal distance traveled. The air resistance will also drag on the horizontal velocity. You actually will have a horizontal acceleration that will be slowing you down due to that air resistance, and that will further reduce the distance traveled. And so you'll see a lower height reached and a much lower range reached due to the presence of air resistance.